On Monday, we stopped on um, the reactions of, we started the reactions of aldehydes and ketones. We've talked about the oxidation reaction that you can perform on them. And then we wanted to start the nucleophilic addition reaction that they participate in. And I showed you these as a general mechanism for the nucleophilic addition reaction you'll be getting with aldehydes and ketones. And we identify some of the nucleophiles that you can use in the process. One more nucleophile that we omitted was water. Well, we've indicated oxygen in alcohols, and it's worth noting that water also can act as a nucleophile. All right, even though it's very, very weak nucleophile, it can act as a nucleophile and add to the aldehydes and ketones. So if you have an aldehyde and you treat it with water, that aldehyde can be hydrated to get okay. So of course it's a reversible reaction depending on the type of aldehyde you're using. The same thing is true for a ketone. A reversible reaction. Okay. So this addition of water to aldehyde and ketone. Okay. All right. This addition can be both acid catalyzed and base catalyzed. Okay. So in the base catalyzed addition of water to aldehyde or ketone, so under basic condition, you know that the water is going to exist in that form. So your hydroxide ion is going to act as your nucleophile that will add onto the electrophilic carbon of the aldehyde or ketone. So now you have base hydrogen. Okay. I'm not going to be showing those dots anymore. But now you know they're there. Okay. So these can pick up proton from the water to regenerate the hydroxide. Okay. So that's for base catalyzed. For acid catalyzed reaction, for acid catalyzed hydration reaction to the aldehydes and ketones, the first step in that process, so here I'm using just aldehyde. You can write the same reaction for ketone, right? So it's the carbonyl functional group that we're focusing on there. So for acid catalyzed, the first step in the reaction is protonation of the carbonyl oxygen. So the carbonyl oxygen is going to pick up a proton from the acid and becomes protonated. Bless you. I should draw that out. Okay. Now, the water molecule that you have there at this point is going to act as a nucleophile. Breaking up the carbon-oxygen double bond. And what you get there is this intermediate. Okay. And water will at this point act as a base to deprotonate that intermediate. Okay. So that's the mechanism for acid catalyzed addition of water and base catalyzed addition of water to aldehydes or ketones. So you can substitute that aldehyde functional group with a ketone and do the same mechanism. And this is the mechanism we're going to observe for every reaction we're going to be considering going forward. Oops. Okay. All right. So now let's look at the first nucleophilic addition other than water. The nucleophilic addition of HCN, hydrogen cyanide. Okay. The cyanide ion, Cn minus, is your nucleophile. Okay, so that's your nucleophile. You can generate Cn minus by treating HCN with KCN. So in some reaction you may see Cn minus written, or you may see a combination of these two. Okay, they will generate, so this will generate okay. Even though it's written as Cn minus, you should know that the negative charge is on the carbon, right? Not on the nitrogen. All right? So the connectivity is very important. So when you're connecting it to a bond, you don't write this. That would be incorrect. That's something else. Okay? It would be written as Cn bonded to whatever you're bonding it to. So the Cn minus is your nucleophile, and it's going to attack your electrophilic carbonyl carbon, breaking up that bonds. Okay, generate intermediate alkoxide, and that can pick up the proton from the HCN to form your product. Okay, this group is called nitrile. We're going to get to that in a couple of days from now. We'll get to that. Nitrile, carbon triply bonded to nitrogen will be nitrile. And because you have in the same molecule a cyano group and an hydroxyl group, these kind of compounds are referred to as cyanohydride. Okay, just like we had halohydride. So these compounds are referred to as cyanohydride. Okay. Halohydride will have halogen with the alcohol, whereas these will have a CN with the alcohol in the same molecule. Okay. Now, what is the chemical significance or synthetic significance of introducing this cyano group into molecules? Well, if you want to increase the functional group or lengthen the chain of the substrate that you're working with, then you can use the cyano group. So for example, the mandelonitrile, yeah, tongue twisting. The mandelonitrile that you form here, which has the nitrile group and the OH functional group, can be transformed to other functional group. So for example, you can reduce it. We're going to talk about the chemistry, more about the chemistry later on when we get to that functional groups. But you can reduce it with lithium aluminum hydride to get an amino alcohol. Okay, amino alcohol are huge functional groups in a natural product, right? So you can get an amino alcohol. So you've reduced this triple bond, and your amine is now formed. So you have amine and an alcohol. So it's not amino hydride, it's amino alcohol. Okay. Or you could hydrolyze. So you can conduct hydrolysis, hydrolyze your nitrile group to get a carboxylic acid functional group. Okay. So these are alpha hydroxy carboxylic acid. They are also good building blocks, getting a larger molecules from a smaller molecule. So at that alpha position, for example, if you have something else other than the phenyl group, let's say you have a straight chain alkane there, you can dehydrate that alpha position to get alpha beta unsaturated carboxylic acid, which can also lead to further functionalizations, right? It will open up the alpha position and the beta position for functionalization. You can grow the chain. So that's the the chemical and synthetic importance of that nitrile groups, right? We're still going to talk more about it. I left a space in the next page to show the mechanism, but I'll define the mechanism for later on. All right. All right. The next reaction we're going to consider is nucleophilic addition of Grignard reagents to your aldehydes or ketone. So it's a nucleophilic addition reaction. So you already know by now that your nucleophile is the alkyl groups or the aryl groups or whatever group you have connected to the MgX. So that's going to act as a nucleophile attacking the carbonyl carbon. The bond will break. You've seen this several times. I'm very sure if they wake you up in the middle of the night to write the mechanism for days, you should be able to do that, right? Okay. So, of course, the first step will be picking up of that, right, to get activated carbonyl, and then the R group can go there. Get your MgBr or MgX removed upon hydrolysis. Just pick up a proton. So you've done a reaction on this in the lab and gone over this several times. So, okay, so that's Grignard reaction. Another reaction that we've talked about for carbonyl is under synthesis of alcohols. How do you make alcohols? We said you can make alcohols from aldehydes and ketones by reduction. Okay, so hydride reduction. So you can use sodium borohydride, you can use lithium aluminum hydride, right? There are some boron reagent that you can use. There's 3. You can use the other reagents, I don't know, sodium cyanoborohydride. I believe this would be 3 or something like that, I don't know. But the sodium cyanoborohydride, is it 4 or 3? Okay, so there are a lot of reagents you can use, hydride reducing agents you can use, but at least for now, you know sodium borohydride, you know lithium aluminum hydride, and you also know dival, right? Or dival H. Sometimes they call it dival H. All right, so that you know. So if you're reducing aldehydes, what kind of alcohol do you get? Primary, secondary, tertiary? What do you get? If you're using aldehydes, if you're reducing aldehydes, you get primary. If you're reducing ketones, secondary. Okay. All right, so let's go to another nucleophilic addition reaction that's probably going to be new to you. Some of you may have seen this, some of you may not. All right, so nucleophilic addition of amine. Remember, we listed all the types, different types of nucleophiles that you can use. Right? Remember, on this page, I showed you the different kind of nucleophiles that you can use. So amine is part of it. Okay. So addition of amines to aldehydes or ketones can give you either imines or enamines, depending on the type of amine that you use, because you can have primary amine, secondary amine, or tertiary amines, right? So depending on the kind of amines you use, you can have either imines or enamines, okay? Just like enols, enamyl is a double bond that contains an amino group, an amine, right? That's why you call it enamines. Okay? So basically, your amino group is sitting on the double bonds. So if you look at these, you have your amino group sitting on the double bond. So that's why you call it enamine. That's the way to differentiate it. But in imine, your nitrogen is part of the double bonds. Okay, so your nitrogen is doubly bonded to the carbon in imines. All right, so that's how to differentiate those two. But how are they formed? Well, imine is formed if you use primary amines, right? Whereas enamines is formed when you use secondary amines. All right? Okay. So we're going to look at the mechanism for the formation of both. Just think about it, okay, as a rule of thumb, right? If you're reacting the amines and the enamines, or amines and the, if you're reacting the primary amine and the secondary amine. In the primary amine, you have two hydrogens connected to your nitrogens, right? Imine reaction with aldehydes or ketone are referred to as condensation reaction. Okay, so they are condensation reaction. You are condensing the two molecules, you are bringing them together. And what happened to the terms, if you use the term condensation, what does that mean?
Take out water.
Exactly, formation of water. Think about it in the room. If there's condensation in the room, it means water is forming on, you know, maybe the walls or something like that, because it's warmer outside or cooler outside, whatever, you know, wherever it's cold, you know that, right? So that term condensation means you're forming water. So how is water formed when you treat an amine with aldehyde? Where do you get that water molecule from? You get it from the two hydrogens that's on the amine and the oxygen that's on the carbonyl. So that's how you get your H2O. All right? That's how you get your H2O. Okay, so that means that oxygen from the carbonyl is going to disappear, and the two hydrogens you have on the amine is going to be given off. Okay, so that's basically the way to imagine that when you're trying to predict the product. So if you look at amine, for example, the oxygen is gone because the oxygen came from the carbonyl, whereas the hydrogens that you have connected to the nitrogen also is gone because it's from the water molecule. So that's how to predict it. You had a question?
I'll ask in recitation.
Okay, you can ask.
I was just going to say if this is what forms peptide bonds.
No. It's different, a little different. In peptide formation, you're talking about acyl substitution reaction. We're going to get to that part. Okay. Right now, we're talking about addition reaction to aldehydes and ketones. So they don't undergo any acyl substitution reaction. In peptide formation, you have your carboxylic acid that you're reacting with your amino group. The carbonyl is not broken, but the nitrogen is substituting whatever you have connected to the carboxylic acid before, and then they form a new bond. Okay, but carboxylic acid itself is unreactive, so you have to use certain catalysts to perform that, and we're going to talk more about that when we get to that section. Okay, so in this case, you don't form a peptide bond. You don't form. So peptide bonds are formed from amido groups, amides. So amides are different from amines. All right, but that's a good thinking. Okay, you're trying to connect everything together. That's good. Keep doing that. It will help. Awesome. All right. So, but for this, we're talking about condensation reaction. Okay. All right. So, what's the mechanism for formation of imines? Okay. Yeah. By the way, could be acid catalyzed or base catalyzed, but we're not going to go into that. Okay, so what's the mechanism for base? I'm just going to use a generic reaction. I'm not going to draw all these out. Okay. I'm going to do the skeletal structure here. And then I'm going to stop at this carbon. Okay. So usually this reaction is done mostly under acidic condition, but you can use base to catalyze the reaction. So the first step, your nucleophile is the nitrogen. Okay, you have the lone pair of electrons on that nitrogen. So that is going to attract the carbonyl carbon just like water would and break up the bond. So now you have O minus base, the nitrogen, the hard groups, and the two hydrogens you have on the nitrogen. Now the nitrogen becomes positively charged, so the net charge on the on the whole molecule is 0, because you have negative on oxygen, positive on nitrogen. At this step, there's going to be a proton transfer, so I'm going to draw the electrons that we're moving to pick up one of the protons that you have on the nitrogen, and the electron will be pushed back onto the nitrogen to get your lone pair of electrons that you need. So this is now neutral, starting back its lone pair of electrons, and then this is H. Okay. Now this is where the catalysts come into play. If you're doing this reaction under acidic condition, now you're going to use an acid. This acid is going to protonate. Oh boy, no, this is just one. I'm sorry. Plus, okay. So the oxygen is going to pick up that proton. Okay, then you have water molecule floating around. Now I have a question. Okay, just so you have two nucleophilic center, right? And two basic center. Why is the oxygen picking up the proton instead of the nitrogen? They both have lone pair of electrons, right? But why is the oxygen picking up that proton and not the nitrogen? What do you think?
Is it more electronegative?
Exactly, it's more electronegative, right? Very simple. If you look at the electronegativity value, I think oxygen has about, I don't know, don't quote me on this, check the book, but I think it's about 3.5. I think it's about, no, I know it's more electronegative, I'm talking about the value, right? Don't quote me on the value. I think it's about 3.5 for oxygen and then 3 for nitrogen, but check that, okay? So oxygen is more electronegative. And another way to look at it is the lone pair of electrons you have available, right? So oxygen has 2, nitrogen has just 1 pair, right? Okay. But there will be equilibrium between both. So once it gets on the oxygen, the nitrogen can pick it back to relieve the positive charge that you have on the oxygen and to be going back and forth. But most of it will be towards the positively charged oxygen. Yes?
I'm sorry, I just can't tell if that's a bond breaking where the H is up by your acid.
Yeah, so we're breaking this bond. That's why I drew this arrow to come over onto the oxygen. So the electron is coming onto the oxygen. That's what the arrow is showing. Okay? Alright, so at this point you can have this can go in 2 ways. Because you have this lone pair of electrons on nitrogen, it can act as a nucleophile, forming a double bond with the electrophilic carbon there, and then the water molecule will be kicked out. Okay, so now you have, this is now doubly bonded to the nitrogen, which has that and a positive charge. Okay, and the water molecule you have floating around here, after picking up the proton from the acid, will again act as the base, remove that proton, and you regenerate that lone pair of electrons on the nitrogen, forming your imine. Okay, forming your imine. So now you have to think about it. What about if you're doing the reaction under basic condition? Where will the mechanism change? It will change over here, right? Because instead of the oxygen picking up the proton from the acid, you have HO minus. That HO minus is going to be picking up these electrons. It's going to be picking up this proton from the nitrogen, right? The electron will be pushed to make a double bond there, and then you kick out OH minus again. So you regenerate your OH minus that you're using as the catalyst. Okay? All right. So, what about enamine formation? In enamine formation, for you to have an enamine, when you're reacting a secondary amine with aldehyde or ketone, that aldehyde or ketone must have alpha protons, right, available. Bless you. Because think about it, you need 2 hydrogen atoms in water molecule, right? Nitrogen is only going to supply 1. You have to get the other one from somewhere. Okay? So that carbonyl has to have alpha proton. Okay? And then you see the role of the alpha protons in the mechanism. So the first step of the mechanism is the same. You have your carbonyl, then you have your amine, with R2, they could be the same, they could be different. R2 could be the same, could be different. So this is going to attach the carbonyl carbon. That bond will break. Excuse me. So now you have hydrogen connected here. It's hydrogen. Okay, so I have the two R groups. Let me just put them this way. Okay, so this is now positively charged. Okay, then again you have the proton transfer onto the nitrogen, onto the oxygen, so you have OH here. Okay. Alright, so at this point, if you're using, again, it can be base catalyzed or acid catalyzed. So if you're using your acid, the oxygen is going to pick up that acidic proton. Okay. Okay, you have that, and then you have the water floating around. Okay, so this water is going to act as a base, and it needs to get a proton, right? There's no proton on the nitrogen to be removed. If it removes this proton here, then it will be going back to that, right? So there'll be equilibrium there, so the reaction is going to be stagnant. So it's going to be looking for where to pick up the proton. That is where the alpha proton that you have on that carbon comes into play. Because that alpha proton now becomes acidic, very acidic, right? So if you look at the distribution of charges here, this is positively charged, so that means this is partially negatively charged at this point, correct? Although it can pick up the proton, this will be negatively, this will be, this will be positively charged because it's stabilizing that positive charge there. That means this will be negatively charged, partially negatively charged. That means this is acidic. Okay, so that's the importance of the alpha proton. So this oxygen will now pick up that alpha proton. This will form a double bond here, and this bond will break to regenerate that water, right, that you use as a base. So what do you get? You have a double bond, okay? You have the amine with its R2 groups, and then what else? What else do we have? And then we have this double bond here, correct? I mean, we have this alkyl group here, okay? So that's how you get your N from alkene, amine, enamine. That's how you get your enamine, of course, plus water, plus acid. So that's if it is acid catalyzed. What about if it is base catalyzed, right? The mechanism is going to change somewhere there, right? When you have this germinal amino alcohol, right? Okay, so at this point, if you're using a base, what your base is going to do is to rip off that acidic proton that you have and then kick out the OH minus, and you regenerate the base that you use. Okay? All right. Okay. So that's all about enamine and amine formation. Any question? Okay. Good. So let's go to another reaction. There's a lot of reactions to talk about, right? But the thing is, if you know the mechanism, it's very easy. Okay, so that's why mechanism at this point is very important. You have to know the mechanism. You have to be able to identify your nucleophile and your electrophile, and then you'll be able to predict your product by moving the electrons around. Okay? Yeah. So the next reaction we're going to consider is Wolff-Kishner reaction. Wolff-Kishner reaction. Wolff-Kishner reaction is a reaction that involves this nasty compound, hydrazine. It's a very regulated compound. But if you look at hydrazine, hydrazine is just like your amine, right? This is hydrazine. So you basically have two amine connected together, two amino group connected together. Okay. So that hydrazine, under a very basic reaction, can reduce your aldehyde or ketone to alkane. Okay, so it converts. Where can we put that? So, right, so it converts aldehyde or ketone to alkane, or reduce aldehyde to alkane. Okay, so when you have a carbonyl in aldehyde or ketone, replaced by two hydrogens from the hydrazine. Okay, and nitrogen will be given off, and you have water formation. So those are two examples there. Here again you have your carbonyl. In this case, this is an aldehyde. This is an example of an aldehyde. That's from the name, and this is an example of ketone from the name and the structure. So that carbonyl is reduced in Wolff-Kishner reaction. So the reagent there is hydrazine and base, strong base. Don't just write hydrazine alone. If you just write hydrazine, what do you form? If you just write hydrazine, what do you think you form? If you treat hydrazine alone with aldehydes or ketone, what would you form? Yeah, but what would you form? No. So if you treat, if you just take your aldehydes or your ketone and you throw hydrazine in there without the KOH, what do you think you'll form? So we said hydrazine is an amine, correct? Mm-hmm. So if you treat an amine with aldehyde or ketone, what do you form? You just said it.
Or amine.
So what will form out of the two? Will it form an enamine or will it form an amine?
Would it be amine because it's not attached to it's a primary?
It will form an amine, because it has two hydrogens on, right? So it will form an amine. Okay, it will behave like a primary amine. Okay, all right. So that's why you need the base. Okay, so mechanism, right? Yeah, let's do the mechanism. Okay. All right. So which one should we choose? Let's choose this. Well, let's choose the simpler one, right? I mean, in structure, right? We can choose this, right? Let's choose that. Oh boy, to draw. Oh boy. Okay, let me use generic, right? I'm just going to use our group to represent these guys. So you can, when you get home, you can practice putting the actual group there, right? So we have the R group, and then we have this, okay? So the first step, of course, is going to be okay, and then this will pick up that proton. This electron will go back onto the nitrogen. There's a positive charge here. Please don't move that out. Base. This nitrogen here. Throw this out so that you guys can see that. Okay, let's throw out the hydrogen here. Okay. So when you're using, this is not just KOH, it's strong, very concentrated KOH, okay? So when you use your base, that's going to take this proton, okay? Put that down. Which way should we go? Let me keep this here. Okay. Now we're gonna have base. Well, when I do that, I'm going to keep these. I don't like that. Well, okay, so let's keep that out. Okay. So now, base. This hydrogen here. Move this there. Okay. 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 I don't like this. Well, we can go that way, that's fine. Alright, so we have the base again. Now I'm going to draw my arrow across a long line, but that's okay. So I'm going to move this over here to pick up that proton. This will form a double bond here. This will break and push that electron on this carbon, okay? I don't like the way I drew it because now the arrow is overlapping with the bond, so but that's okay. At least you see what I drew there. So now you have the double bond here. It's nitrogen, this hydrogen, small pair of electrons. There's an hydrogen here. We've created a carbon ion here. Okay? This is negative charge. Alright, so that carbon ion is going to pick up the proton that was on the water, and you regenerate the base. So I'm going to draw a base out here. So now you have this hydrogen and that hydrogen. Okay. And you have the nitrogen. Actually, so that's not messy. We have this double bond. We're going to move this hydrogen down here because I want to pick it up. Okay. Nice. Alright, so now the base that you regenerate here will again pick up this proton. You will generate a triple bond between the nitrogens. This bond will break, pushing the electron again onto that carbon. And this is how you get your nitrogen that leaves as gas. So it's N triply bonded to N, that's your nitrogen, okay? So water is still in play. This carbon ion will pick up that proton, you regenerate your base, and you get so you get your base there. But usually the reaction will be quenched using an acid, right? So when you throw in an acid, this can pick up the acid and then you get water. And that's how the water from the reaction object comes into play, all right? So, but we don't care about the nitrogen and the water. We're only concerned about what do you get when you treat that carbonyl with hydrazine under basic conditions is your alkane.
Where did the methyl group come from?
The methyl group, I'm just showing the carbon there. So instead of drawing, I want to do the skeletal structure. Do that, right? Okay. So that's the mechanism for wolfification. Okay. Oh boy. We have 6 more to go. Oh, by the way, I've modified our syllabus, right? So I've removed chapter 727. Okay, so look at the updated one. We'll stop here for today. Wow, there's more to go. Wow, that's so slow.
In the reaction, it shows methyl or like an alkyl being attached.
Sorry?
In the reaction, it shows that alkyl group is attached, not just a hydrogen.
It should.
You go up.